Hello, welcome to the next GDCh and ChemistryViews video. Today we have with us Professor Paul Anastas and Professor John Warner.
Thank you very much for having us.
Yes, very happy to be here.
Welcome. And the GDCh just honored you with the August-Wilhelm-von-Hofmann-Denkmünze. So what does it mean for you to receive this award?
Very, very proud for the green chemistry community. There are thousands of people worldwide that have embraced the principles of green chemistry and have dedicated their careers to this. So I'm very proud that Paul and our names are associated with this. I feel this is recognition of the field of green chemistry and the many practitioners worldwide. And so very proud.
I completely agree with John. I think that any award really doesn't recognize people. It recognizes actions. And so right now there are so many actions being taken to advance green chemistry. Some of them are at the laboratory, some of them are in the classroom, so many of them are in industry. And it's those actions that I think are really being recognized by this wonderful Hoffman Prize.
Mm-hmm. And we have to come back to that. But first I would like to know, do you have a connection to the GDCh, and or what kind of connection do you have to the GDCh and Germany as a US chemist?
Yeah, I think that both John and I started out certainly as synthetic organic chemists, and any synthetic organic chemist has to have a respect, a knowledge and awe of German chemistry. And so we started out there, and just have so many colleagues and friends in Germany. But of course, John has a much closer relationship.
Yeah, so the German Chemical Society and German chemistry is fundamental to the field of chemistry. You know, the roots of chemistry come from the amazing German chemistry of hundreds of years ago. I've been very fortunate, you know, the American Chemical Society has a very close relationship with the German Chemical Society, and there are exchange programs where students from the US have gone to Germany and students from Germany come to the US, and I've hosted teams of chemists at institutions that I've been at, and now I have a close relationship with the Technical University of Berlin, and so working very closely with the green chemistry program that's there. Yeah.
At the Technical University of Berlin, there is the John Warner Center for Chemical Innovation, I believe.
Yeah,
yes.
Thank you.
Yeah, so would you like to say a few words about that?
Yeah, no, it's very proud and honored that it's changed its name. The German Ministry of Economic Affairs and the Technical University of Berlin named the center, it's a chemical innovation factory, which combines startup mentality, entrepreneurship, and green chemistry, and it's created a center at the Technical University of Berlin that is working with young scientists that want to be entrepreneurs and to create startup companies.
Mm-hmm. And why is that in Germany? Or is there a reason?
Well, because the people there are amazing and they wanted to do it. And I'm just very, very proud of it. That it's something that happened spontaneously at that university, that a group of students, a group of faculty, and some people from the government said, we should do this. And one day I got a phone call saying, we want to do this and we'd like to have your name on it. And I was just very, very honored. And, you know, just it's amazing. Mm. Yeah.
Mm. And then coming back to the 12 principles of green chemistry, and yeah, you laid the foundation for sustainable chemistry. And how did this all start?
Oh my goodness! So many years ago, I think when you talk about the start, you have to go back to looking around in the early 90s and seeing the way that things were done in chemistry, and just saying we can do better. You know, when we laid out the 12 principles of green chemistry, it was greeted with a lot of enthusiasm. It made quite an impact. But I would suggest that it wasn't because it was brilliant or insightful, or it's that it was obvious. It was devastatingly obvious that this is how we should be doing things, and it bore very little resemblance to how we were doing things at the time. And so that is how the 12 principles, I think, really formed. Would you agree?
Yeah, so if you go back in time, to say 1990, and you look at every university in the world, you look at the courses, the classes, the examinations that a student was required to take to become a chemist, you would find very few. There were some, especially in Germany, there were some, but very few universities of the thousands and thousands of universities that would give someone a diploma or a degree and say, go out in the world and invent the future. No one required any knowledge of how to anticipate if something is toxic, if something is biodegradable, if something contributes to global warming. It was absent not only from the curriculum, but to the self-definition of what it means to be a chemist. Now, the non-chemical community finds that impossible to believe, that they would imagine that the first thing you learn as a chemist is how to avoid hurting yourself or avoid making toxic things. And when people realize that the field of chemistry does not have that as a fundamental part of the curriculum, most people, when it go, oh my God, we should have that as part. And so it becomes so obvious that it's almost impossible to imagine that it wasn't always here.
And how was that taken up during that time then?
So it was really interesting because what happened was people who wanted to do green chemistry did the things that they were most familiar with and most comfortable with. So we saw so much in the area of new solvents and new solvent systems, and of course catalysis was very big. But over time, people understood, or came to understand, that the 12 principles were a cohesive system, not principle by principle, but across the entire life cycle, from the origin of the feedstocks and materials all the way to final product and everything in between. And of course, how that final product can be transformed into new feedstocks. Mm-hmm. So what was interesting is some things were quite obvious and comfortable to people. Other things took quite some time to understand. So even though there are papers and chapters and things that we've done over the years about, one's entitled, When is a Waste Not a Waste? And that was so many years before, this talk of circular chemistry. Mm-hmm. When is a waste not a waste? When it's a valuable feedstock. Mm-hmm. So it was embraced right away, but has evolved as people's understanding has become deeper and deeper.
Yeah, because one way of thinking about it is, people have always cared about human health and the environment. It's not like 50 years ago chemists didn't care, but we felt 50 years ago, 40 years ago, 30 years ago, that chemistry, by definition, had to be dangerous. It had to be toxic. If you choose to be a chemist, you must accept that there are certain dangers and hazards associated with it, but we use engineering to protect people. We wear masks to protect our lungs. We wear goggles to protect our eyes. We install all this equipment in a factory to make sure it doesn't get out to the land, the air, and the sea, and we've accepted that. Green chemistry questions, do we have to accept that? Is it an innovation? If we have a red dye that coats a textile, but it also is a carcinogen and causes cancer, must it cause cancer? Or is that a chemistry challenge to invent that red dye to not cause cancer? Now, from an industrial perspective, every time you have a hazardous component, there is enormous cost associated with it, because now you have to pay for the engineering to protect it. You have to train people to deal with the hazards. There is liability and legal costs and regulatory costs. So industry, every time industry does green chemistry, they save money and are more profitable. So green chemistry just makes so much sense. But if people learning chemistry at the university don't learn what makes a molecule toxic, what makes a molecule hazardous, how do you invent things that aren't? And so there's a very logical thing. Of course, green chemistry doesn't say that you should want these things. The world already wants them. Green chemistry tells you how to meet those things. That's what's so special about green chemistry, is it's not a description of desire. It is a way, a pathway to achieve those goals.
You know, and it's such a good point, because we've moved from just taking hazard as a given, something that had to be accepted, and turned it into something that I think we both say, hazard is a design flaw. That if your chemistry results in hazard, then your job in designing is not done. It is a flaw that needs to be fixed. So that's a big shift in the way we've thought.
And why this is so important to the field of chemistry is because this generation of students cares deeply about the environment and what's happening in the world, the social issues. And when the best and brightest students are young and they say, what do I want to be when I grow up? Chemistry is not on the list of these socially minded students unless green chemistry is part of that equation. If they feel chemistry must be causing the problems, they will go into other fields. If green chemistry teaches them that this is part of the solution to these problems, now all of a sudden we have the best and brightest students coming into chemistry. So the future of chemistry, I think, is so exciting because of this new group of students that have this passionate environmentalism, and they choose chemistry, whereas one could argue that absent green chemistry, the field of chemistry looks at the bad guys, the people causing the problems. And so now there is no sustainable future without people inventing those technologies, and those technologies will be invented through green chemistry.
And do you think we have enough education, or education is good enough for our students in that field?
It's amazing how much advancement has happened over the last 25 years, but it's not enough. You know, there are still many universities that have green chemistry as an elective. I would say that when we first started at green chemistry, no one was talking about it. There were no universities. And after about 10, 15 years, I would say there was a lot of green chemistry that was happening here and there. Now, most universities have one or two faculty members that are passionate about green chemistry. And if students have those faculty members, then that's wonderful. They have been lucky to have that. But having chemistry departments embrace it as a required component is just at the beginning stage. That's where the organization called Beyond Benign has what's called a green chemistry commitment. And there are about 100 universities worldwide who have signed that commitment, saying that this isn't an elective, it is part of the required curriculum. When all universities that give degrees in chemistry require green chemistry, our work is done.
But at the moment we see with climate change, for example, that time might be running out. We don't have that much time to wait another 20 years until we finally reach a goal where we say, yeah, no, I don't know, we accept all the 12 principles and we really live like that. So do you have idea, or is that not your opinion? And do you have ideas how we could speed this up, or maybe combine the whole chemistry community to speak more with one voice, to think more unified about these things?
Imagine a magic wand. Tomorrow morning, every person in the world insisted on only having sustainable technologies. Every retail store insisted on selling only sustainable technologies. Every manufacturer insisted on only manufacturing sustainable technologies. We would say, wonderful, we've achieved all of our goals. The problem is, in my opinion, 70% of the solutions have not been invented yet. So this is not a crisis of a desire. It is a crisis of innovation. We need to get in the lab and as quickly as possible create these technologies. I think the mistake a lot of people make is that they think this is still about convincing people to want to do it. I think there's still a little bit of work in that direction, but delivering on those needs hasn't been achieved yet. And that's where if every chemist learns how the fundamental molecular science of sustainability, what I'll call green chemistry, if they have those tools, if they have those skills, no matter where they work, whether they work in petroleum industry or the dye industry or the pharmaceutical industry, the cosmetics industry, they will make it better. But you don't improve the sustainability of a technology just by wishing it. You must have the fundamental chemistry skills to go in the lab and invent it. And that's where we need to do more work to get funding agencies to be funding this type of thing so that universities have the students that are being properly trained.
Mm-hmm.
So I completely agree. I think it's so tremendously important that we recognize that there's a very hopeful vision of the future. I'm a believer that we can have a society where the material basis of our civilization, of our society and our economy is healthful rather than toxic, that is renewable rather than depleting, and is restorative rather than degrading. We can have that, and the path to that are the principles of green chemistry. And so when people understand that that's possible, they immediately ask how. How do you do that? How do you achieve that? And you say, well, here's a roadmap. And so, you know, green chemistry, we say it's the chemistry of sustainability because it is chemistry. Now, will chemistry alone bring us to that future? No, that's where all of the partnerships come in. You have to have partnership with industry, with government, with not-for-profits, with civil society. You build these so that you can implement these solutions at scale to make this happen on a societal level. But it has to start with the chemistry. So, well, I always say that chemistry alone won't solve all of the problems, but in the absence of chemistry, I don't see a path to solve the problem. So it is central and essential.
Yeah. Yeah. So imagine you are a company, you have a product, and you are offered a technology that works better than the current product that you sell. It has better cost than the product that you currently sell, and it achieves sustainability goals. Can you imagine a world where anyone would say no thank you? So if that is so obvious, something that works better, costs better, and is better for human health and the environment, everyone would be using it. So the fact that they're not means that it doesn't exist. And so the crisis here is to find a path to invent those technologies so that the companies will use it. And that's a skill problem. You know, like I said again, we need more than just wanting these technologies. We need to train the future practitioners with the skills to do it, to accomplish it.
Okay, and if you look at your research and what you've done, what are the things you're most proud of or you think are very special?
I'll let John go first.
I mean, they all probably are very special.
Yeah. You know, it's interesting. It's like asking me, you know, which of my children are my favorite children. Yeah. You know? But no, I've been blessed to have a career that has been filled with so many people helping me. And that there's just been an amazing group of people that I've always been blessed to work with. And, you know, one of my proud things is the Warner Babcock Institute for Green Chemistry. The Warner Babcock Institute for Green Chemistry is an organization that in the last 12 years, has filed over 300 patents. It has spun out several companies. It has a pharmaceutical company with an ALS drug designed by the principles of green chemistry. It had a photovoltaic company that Amazon has just invested in, and we got manufacturing in California of a photovoltaic system for indoor harnessing of photons that's designed by the principles of green chemistry. There is a asphalt paving technology called collaborative aggregates that allows you to use 100% recycled asphalt in repaving roads, designed from the principles of green chemistry, and a hair color technology called hairprint that is based on the principles of green. So these amazing inventor people that have been able to take deep chemistry science that could be in wonderful journals and publications and turn it into products that work better and cost better, and actually form companies that are now selling this in the real world. That arc is so critical to see that the world is embracing these technologies. We just need a mechanism to do more of it. And so that's the way I'm very proud of. And it's not just me. There are so many organizations and people doing amazing things.
So I'm lucky to be part of the Yale Center for Green Chemistry and Green Engineering, and there's just so many folks that have come through our center and are now faculty members around the world. So being able to work with these students and who turn into wonderful professors is probably the most fun for me. In terms of the research that we've done, we try to look to the future. So we genuinely believe that the future is going to be not the same kind of reactive toxic reagents that we've been using for the past 200 years. But the future is going to be photons and electrons. So it's not surprising that we do a lot of photochemistry and electrochemistry. We believe that the future is going to be around transforming waste into value. And so we do a lot with agricultural waste and forestry waste and making new materials. We do a lot with taking on our greatest waste right now, which is CO2, and transforming that into value. We also think that the future is going to be really all about design. And so the idea of how you design molecules from first principles so that they can't be hazardous, they can't pursue different toxic mechanisms, and we're developing a lot of computational models and rule-based systems to do that. And so these are some of the paths to the future that we try to engage in and that are so rewarding. Yeah.
And I guess you both have a very positive view to the future, because in the membership magazine of the GDCh, you both answered in an interview that if you could be somebody else, you would be somebody in the future.
It's so true. Yeah.
No. The best, I must believe the best days are in front of us. Yeah.
That's true. It's the only thing that gets you out of bed in the morning.
Exactly.
The pessimism doesn't motivate.
Yeah,
you know.
exactly.
So.
And there's an overabundance of pessimism. We're not helping the world by contributing to that.
I do have to say, we were chatting a little bit, and we both enjoy science fiction. And we were talking about how when we were growing up in the late 20th century, 20th century science fiction was so hopeful. It was so optimistic. It was about, discovering strange new worlds and jetpacks and flying cars, and it was just wonderful. Yeah. And if you look at science fiction today,
it's all about bad.
Post-apocalyptic, dystopian, just terrible. And you say, hold it, was it that the 20th century was so wonderful and a happy place? You say, no. I mean, there was abject poverty, there was the threat of nuclear annihilation, 100 million people plus perished in war. So what is the difference? And the difference really is about a perspective, about how you view, how you envision and visualize what the future can be. When we were young, the most hopeful phrase that you could hear was, anything is possible. Now, today, the most terrifying phrase you can hear is that anything is possible.
Yeah.
And so we need to bring this perspective of what is a future, not utopian, or because it's just too unattainable and unrealistic, but not dystopian, that is to be dreaded and paralyzing, but something that that I call newtopian. Newtopia would be something that's realistic, possible, and worth striving for.
Yeah. People, I get very sad when people say that chemistry is a mature science. I feel that we are just on the frontier of chemistry. That yes, we've been doing it for 200 years, but the future, what chemistry is going to be in the future is going to be so different than what chemistry is today. This is in my opinion, the best time in history to be a chemist is today, because there's so many new opportunities, there's so many new directions that now people are recognizing how chemistry is part of all aspects of human endeavor, and that we have such an important role to play. And so, what's so important to me is that we chemists rise to this need. And we don't say, oh, chemistry is the same as it has been for 50 years and it'll be the same in 50 more years. We need to embrace change so that we can be part of this future and help drive a truly sustainable future. It won't happen without chemistry.
So chemistry is just getting started, and it's amazing that people ask me, I'll often get this question of, where did you come up with this name, green chemistry? And it's so interesting, because when you think about the different meanings of the word green, one of them is young, fresh, new. So green chemistry means that it is constantly young and inventive and creative. And so to me, that meaning of green is part of the reason for this phrase, green chemistry. Now, it's also true that green conjures up images of the environment, and in the United States, it is also the color of our money. And so you say, how do we achieve all of our goals of sustainability and environment and health at the same time as we're making it profitable? And so that's really where so much of this reason that the term, the two words, green chemistry, are important. Because if you walk down the street and you ask people, what's the first thing you think of when you hear about chemistry and chemicals? It's toxic, right? And hazardous and dangerous. And so by introducing into the lexicon, into our language, the phrase green chemistry, it causes people to pause and say, oh, that's a little different. And you start a conversation just with that phrase.
Exactly. If it was safe, if it was a word that people already had a meaning for, and I don't think it would be as effective. And as Paul mentioned, it's like today chemistry is scary. It's like the monster under the bed. People are worried about this as being a carcinogen, this is hurting the environment, this is doing this, doing this. And when chemistry is actually visible to people philosophically, it's almost always for a bad reason. It's not for a good reason. And green chemistry changes that conversation to the non-chemical community. It's a way of interacting with society.
So I hear that we need a positive vision and to be innovative and see that we can transform this into industry, our good ideas,
Yes.
and bring it into the public.
Absolutely,
Yes.
and bring
Yeah.
this to scale. Bring it so that it touches every life, every business sector, so that we can really use the power and the potential of chemistry to bring about the sustainable world that we all want.
I think that's a good word for the end, but I didn't want to interrupt you.
Yeah, so the image that I like to conjure up is there are many different blank chemistry. Take whatever word you want. There's a book, there's a paper that's been written about it. And it's almost like here is chemistry, it's this sphere of knowledge that is expanding and expanding in a spherical geometry. And someone defines some type of chemistry, makes a target in hopes that some of that chemistry hits that target. And then someone comes up with another word and here's another target that does that. I don't feel green chemistry is a target. Green chemistry is pushing and shaping the sphere of chemistry so that more chemistry hits those targets, as opposed to making another target and defining another target. It's changing what we think, what a person thinks chemistry. So if I were to hold an Erlenmeyer flask up in front of you, and it was a glass of a liquid, and I would go to a group of chemists, I would go to a group of CEOs of companies. I would go to some, people off the street and say, what would you do to describe this material? Someone might say it's a solid, it's a liquid, it's a gas. Someone say it melts at 100 degrees centigrade, it freezes at 0 degrees. Maybe it has a certain pH, it has a certain viscosity. But most people will not say it's not toxic. We'll say it doesn't harm the environment. If toxicity and ability to harm the environment is not at the top of our mind as a description of matter, and chemists aren't trained to see that as self-definitional, then whose job would it be, if not chemists? So that's my litmus test. The day we can go to a bunch of 12-year-old children and ask them, what is chemistry? How would you describe this material? And they do the solid, liquid, gas, and all that. And they also add, it hurts the environment or it's not toxic. Now chemistry has matured, and now it's a mature science.
Okay, so thank you very much for the interview.
Oh,
Yeah, thank you.
Very nice talking to you.
a real pleasure.
Yeah,
Thanks
pleasure.
so much.
Yeah.